Hello everyone and welcome to the NPTEL course in Pharmacognosy and Phytochemistry. We are learning about interesting set of oleaginous compounds called as lipids and volatile oils, where we are dealing with fixed oils, fats, waxes and volatile oils. In the previous session, we studied what are volatile oils, what are fixed oils, what are fats and what are waxes. In this session, we will learn little bit about their evaluation parameters as well as some of the methods for processing of your fixed oils. So, let us start with the analytical parameters, especially for oils and fats. Now, if you see oils and fats are triglycerides in their composition. They contain both saponifiable as well as unsaponifiable matter. So, if we have to evaluate any oil or fats, few parameters or few physical constants that we can look for are first thing viscosity. Now, in the previous session, we discussed that depending upon their chemical nature, we can have triglycerides containing saturated fatty acids or we can have them containing unsaturated fatty acids. Those containing more amount of saturated fats tend to be solids, and those containing a good amount of what is called as monounsaturated or polyunsaturated fatty acids tend to be more fluid. And also, depending upon their nature, we could classify them as drying oils and non-drying oils, or in some cases semi-drying oils, depending upon their ability to oxidize and form film. So, there are some oils which are very viscous and there are some oils which are very fluid. Some oils which solidify, such as coconut oil, you can evaluate them based on their viscosity. The second parameter is specific gravity. So, if you see most of the oils or oleaginous ingredients, they have their tendency to float. That means they have a specific gravity which is lighter than that of water. Now, comparing between again your oils and fats, your oils tend to be lighter than water, but they will be definitely heavier when you compare them with your fats and waxes. Fats and waxes, the specific gravity tends to be little less. So, if I am talking about a fixed oil, I might come across a specific gravity value ranges somewhere close to 0.99, 0.98, 0.96, whereas when I am talking about your waxes or fats, I might come across something very lighter like 0.95. In some cases, the value may be till 0.88 and so on. So, the specific gravity changes depending upon their nature. Now, when it comes to refractive index, definitely they are more refractive when compared to water, with on an average the refractive index values ranging somewhere between 1.42 to 1.47. Now, here also you will see that compared to your fixed oils, your volatile oils are more refractive or have a higher refractive index. So, if I am talking about 1.46, 1.47, the higher range is generally for the volatile oils. And the last evaluation parameter what you can check is solidification and congeal point. Now, depending upon how much saturated fats are there, how much unsaturated fats are there, and it is a blend, it is not going to be a single compound, and as a result every oil will have its own solidification and congealing point, and that is the evaluation parameters. Now, if you go to see chemical constants, they help us determine numerous criteria. Let us start with something as simple as iodine value. Now, we know that iodine value is actually the amount of iodine absorbed by 100 parts, say 100 grams by weight of sample, which could be a fat or oil. So, why would any sample absorb iodine is when particularly there is an unsaturation. So, across this unsaturation, your iodine might get added, and more the unsaturation, higher will be the iodine value. So the iodine value measures the degree of unsaturation. Higher the iodine value means higher unsaturation. So if I am again trying to balance between oils and fats, who will have the higher value? Any guesses? So it will generally be oils which contains more amount of PUFA that will have your higher iodine value. Now coming down to saponification value. Saponification is a process where you create soap from a free fatty acid. So we know that we have triglycerides in our fixed oils and triglycerides in our fat. Now our intention is to take them and convert those free fatty acids into soaps. Free fatty acid soaps are as good as representing, say for example, I am having a fatty acid and I put it as, say for example, COOH. So rather than OH, I will have a O, potassium or sodium depending upon what salt I am adding here. So if it's a triglyceride, this 3 happens into thrice. So 3 times it will absorb or 3 times it will take. So how much milligram of potassium hydroxide actually is required to neutralize the free fatty acid which comes from hydrolysis of this triglyceride is called as the saponification value. This is generally done as elevated temperature or little heat might be applied in some cases where you want to break the triglycerides. On the other side is if you just want to determine how much free acids it contains, the next value is called as acid value. So apart from triglycerides, in some cases the oils will also contain free fatty acids. Now free fatty acids or determination of free fatty acids is very important because more the amount of free fatty acid, the higher is the chance that your oil will turn rancid. So rancidity parameters can be directly correlated with free fatty acids, and imagine if these free fatty acids are the unsaturated free fatty acids, in that case you will have even more chances of rancidity occurring. So in order to get an idea whether the oil is prone to rancidity or not, after saponification one can even determine a simple, just don't hydrolyze the triglyceride, just react potassium hydroxide with your oil as such at room temperature, whatever amount of potassium hydroxide or whatever milligram of potassium hydroxide is required in the titration, that is required in order to neutralize the free fatty acids which are present in the sample, especially 1 gram of sample, that is what is called as your acid value. Now the next one is the ester value. So if you see saponification value, it gave you amount of fatty acids which are there in your triglycerides plus acids, free fatty acids. So saponification is actually an indicator of triglycerides which had 3 times your fatty acids, if I say, plus it also gave you an indicator of free fatty acids. Now if you determine acid value, your acid value is just going to tell you your free fatty acids. Now if you subtract the free fatty acids or if you subtract the acid value from the saponification value, you will come to know how much amount of acid is involved in esterification. So what I am doing is I am just taking saponification value, okay, and from saponification value I am going to deduct the acid value. This is acid value. What I am going to get is this, how much amount of fatty acids are actually involved in ester formation, and that is what is called as ester value. So in terms of chemical constants, you have iodine value to give you saturation, saponification value to tell you how much fatty acids are involved both in free form as well as triglycerides, your acid value which will just tell you amount of free fatty acids and that can correlate to your rancidity, your ester value which is simply how much amount of fatty acids are involved in triglyceride formation, which is nothing but a difference between saponification value and the acid value. The next set of parameters are what is called as unsaponifiable matter. Now, whenever you take your oil, you might have been hearing that this oil contains vitamins, this oil contains oryzanol, this oil contains something which is very healthy such as your pigments, antioxidants, or some of you might even heard of tocopherol, vitamin E derivatives. So this oil is rich in vitamins. So what are this? The compounds apart from fatty acids which do not undergo saponification are all termed together as unsaponifiable matter. So unsaponifiable matter is the amount of matter or is the weight of substance which does not undergo saponification and then is lipid soluble. So after the soap is formed, what you need to do is you just take your organic solvent, put it in the saponification reaction, and whatever has dissolved now is all your lipophilic ingredients which have not gone saponification. So all this you all take and maybe heat it, you will get what is called as unsaponifiable matter. So good example of that is your lignans which is present in your sesame, your vitamins, tocopherol derivatives, vitamin A, vitamin E, your pigments and your sterols. All of them are categorized as unsaponifiable matter. The next set of chemical constants which you determine for oil are your hydroxyl value, acetyl value and peroxide value. So what is this? So say for example your compound such as, this is an example of ricinoleic acid, and now ricinoleic acid has a hydroxyl group. I want to determine how much hydroxyl groups are there in my sample. So what I do is I maybe react it with acid, say for example I react it with acetic acid, and then as a result I convert this into an ester. Okay. So I convert this into an ester. So what happens in the process is I have acetylated it. Now later on I will hydrolyze and I will see how much acid reacted. The amount of acid reacted can tell me how much amount of hydroxys are present, and that is what we call it as hydroxyl value. So hydroxyl value is the amount of KOH that is required to neutralize this acid which was combined by acetylation to 1 gram of sample. Okay. Now in some cases you can also determine what is called as acetyl value. Acetyl value is generally obtained for fat samples. So it is the number of milligram of potassium hydroxide which is used to neutralize the same acetic acid which is freed by hydrolysis of acetylated fat or even 1 gram of sample. So say for example castor oil, the value might be as high as 150 because it has resinol. But in some oils which do not have hydroxys group commonly present, the oil may be or the value of acetyl value may be as low as 3 to 15. The last value is again important, and that is called as peroxide value. Now what happens here is, imagine your unsaturated fatty acid. Now over a period of time it will tend to form epoxides. These epoxides might even form peroxides. Now what happens in the process is you will get peroxide derivatives. Eventually the molecule will break, gives you aldehyde ketones. We term that as rancidity. So peroxide is somewhere an initial step, we can say, towards rancidity wherever the oxygen is taken by the oil for the process of converting it into a smaller fragments. So how do you determine this? The peroxide value is done or determined by iodometric titration. So here what is done is maybe you release the peroxides, allow it to react with acid in presence of potassium iodide, and the amount of iodine release can be titrated with your sodium thiosulfate. Now since these values are very less, rancidity is very less, if you see comparatively in most of the cases what we have done is we just taken 1 gram of sample, but for rancidity, or that is the peroxide value determination, the amount of sample required is pretty high. So if you see refined oils, it's good, but if you want to use it for parenterals, the oil should not be rancid at all. So for like 1 kg or 1000 gram of sample, the rancidity, the peroxide value should be as less as 5, and even fish oils it should be less in order for its safe consumptions. The next set of value is also a rancidity value, where you can determine how much aldehydes are formed. Like we saw previously, whenever the peroxide breaks, it will give you eventually an aldehyde. Now this aldehyde can be a small aldehyde like epihydrin or malonaldehyde being formed. Chris test is a test which allows a reaction between malonaldehyde or epihydrin aldehyde, fluoroglucinol. When reacted with oxidized fats, it will give you a reddish coloration, and that reddish coloration will tell that whether it's almost on the verge of rancidity or is it oxidized or not. The other sets of values gives you interesting what are called as fatty acid determination. The first one is a Richet-Missel value. Now Richet-Missel value is a value which will tell you how much volatile water soluble fatty acids are there in your sample. So what you have to do is you take a sample, you steam distill it. Now when you distill it, all the volatile components will distill out. You collect the distillate, and that distillate is titrated with potassium hydroxide. Now once the distillate is titrated with potassium hydroxide, what you get is a set of water soluble volatile acids which have come out during the distillation process. So that value, if you take 5 gram of your sample, the amount of KOH which is required to neutralize the fatty acids is determined or is known as your Richet-Missel value. On the other hand, Polensky value is something which is used to determine what are called as water insoluble but steam distillation. So in some cases what happens is, when you distill your 5 gram of fat, you might come across a distillate which separates into a layer, and if that layer is a water insoluble layer, and when you want to titrate it, you use alcohol to dilute it so that it dissolves. So when it dissolves and when you titrate it with a n by 10 KOH, what you get is a amount of water insoluble but steam distillable fatty acids. In that case, you get what is called as Polensky. So this sample is hydrolyzed and then subjected to distillation. So you get amount of fatty acids which have been involved in the triglyceride formation as well. The last one, if I have to determine how much rancidity is actually present, I can do it colorimetrically using what is called as anicidin value. So I take my oil sample, I solubilize it, and then I add anicidin. Now this anicidin reacts to form a colored complex, especially with ketones. This is generally used for determination of fish oil such as cod liver oil. And if I see the absorbance at about 350 nanometers, the intensity of absorbance will tell me how much amount of anicidin is actually present. Now let's go to the next step. After we finish the evaluation, how do you extract oils? Now for the purpose of extraction of fixed oils, it can be done by 3 simple techniques. The 3 simple techniques include cold press. You must have heard of mechanical press, or you must have seen a sugarcane juicer. So you have machines which are set of grooves, and you put your raw material into it. If the raw material contains sufficiently high oils, say for example your castor, your groundnut, your sesame, they contain almost more than 30% of their weight of oil. So when the seeds are so high in oil, if you just put it in your ghani or your press, you will see that the oil extrudes. This is easily done, and when the oil content is high, you can use a cold press. But if the oil contents happen to be little low, you have to facilitate the process of extraction, and that facilitation can be done by heating. So what you can do is either you steam the seeds. What happens during the steaming is the cells swell, the oil globules congeal and eventually facilitate. So same way, or in some cases it is done as elevated temperature, or even your mechanical presses, the plates are at higher temperature. So higher temperature, it's called as hot press, and in the hot press the meal also, the seeds or the plant part from which the oil is to be expressed, gets heated. Because it heated, all the oil kind of congeals, collects together, easily separates out, and you can have a more yield of oil coming out. The last process is solvent extraction. This is done for substances which contain very less quantity of oil. So even if you squeeze it, press it, or even if you heat it, if your plant is not leaving the lipid substance, one good property of solvents we know is like dissolves like. So what you can do in this case is use lipophilic solvents such as hexane, petroleum ether, which are very inert. And using this solvents, if you dip your drug into that, all the lipids will get dissolved in this solvents. Now you filter out, and that filtrate, what you're going to do is from that filtrate you will evaporate the solvent. Now hexane, petroleum ether and all the solvents have a very low boiling point. They are thought to be volatile, whereas your fixed oils have a very high boiling point, sometimes even crossing 300 or 250. So they can easily withstand temperature, and when you heat it, your solvent will vanish and what is left is your oil. So these are the few easy ways which the industry does to extract fixed oil from the samples. Now once the fixed oil is obtained, in some cases they are still considered unfit for consumption and they require some subsequent treatment, and that subsequent treatment is called as refining. So maybe you must have heard of this term called as refined oils. So let's see what refining is. So refining of oils can start with a very simple step, that can be settling. Say for example, I take the coconut endosperm, which is your dried copra, I press it. Sometimes what I get is something like a coconut milk. So what happens is it will take time for the oil and water to separate out. Now, or in some cases there are some solids which will make my oil turbid. I need clear oil. So what will I do is those particles I'll allow to settle. So separation and settling, we call it as aging of oil. So after expression, your oil is kept in a settling tank for a while to let the water phase, to let the moisture or to let the solid particles separate out. This process is called as settling, and often the first step after the cold oil or the hot drawn oil is obtained. Once that is there, in some cases heating is also done. Now heating serves the purpose. In cases when there is moisture, heating will remove the moisture. In some cases when there are odorous principles which are present and this odor is not desired, heating will help us remove that odorous principle. Heating can help us in denaturation of enzyme. So if you take for example rice bran oil, or if you take castor oil, these oils contain oleaginous enzymes such as lipases, and lipases have the ability to hydrolyze and to degrade your triglycerides. Now if this happens, I am having a good chance that my oil will turn rancid. So heating is done in order to denature the oil and to dry it of any traces of moisture which is there. So the oil is taken, heated at to about 200 to 50 degrees Celsius, where it is generally stable. So the oil, water components vanish, the enzymes get denatured, and any other unstable impurities is there. In some cases it might also kind of coagulate with that protein and settle down. The third process which is used in the refining is called as winterization. In some cases what happens is other lipophilic ingredients which are not required in the oil also enter in. So in that case what I need to do is I'll take my oil and slowly cool it down. Now what happens when I cool it down is there are some impurities which will become insoluble. Why? Because their melting point is in that range. So say for example, if I cool something to 0 degrees Celsius, my castor oil normally doesn't freeze at 0 degrees Celsius. But if my castor oil contains some ingredients which will solidify, whose melting point is close to 0 degrees Celsius. So when I am dropping the temperature to sub 0 degrees Celsius, I'll see some ingredients with those kind of melting points solidifying once again. So during the solidification process, I get rid of stearins and other solid impurities which would otherwise precipitate in my oil. So that is called as winterization. This is generally done for fish oils also. Then neutralization. Neutralization refers to treatment of free fatty acids. Now we know that fatty acids are involved in triglyceride formation, but in some cases they remain available as such, rendering the oil slightly acidic, and these free fatty acids make it prone to rancidity. In order to get rid of this free fatty acids, what you can do is you can treat it with a lye, or like sodium hydroxide, potassium hydroxide, or just treat it with sodium bicarbonates if it is very mild. And this treatment helps in removing or neutralizing the acids which are there. So neutralization is a treatment which is often given to remove or get rid of free fatty acids. Next one is degumming. Often you will find that components such as lecithins, phospholipids, they all enter in and they act like a emulsifying agents. So they make a gummy exudate, or they are left as a gummy layer. Now what we can do is, in some cases it is treated with water because carbohydrates are water soluble. In some cases it can be even treated with citric or some acids such that those phospholipids are broken down. In some cases this can even be done with enzymatic treatments. So all of this will get rid of your phospholipids or gums or mucilaginous substance which would otherwise interfere with the clarity of oil. Once that is done, the last part is you can do a charcoal treatment wherein most of your pigment impurities are adsorbed on the charcoal columns. So you can pass your oil through charcoal columns and do that, or even fuller's earth or even silica. This kind of beds are created, either charcoal beds or silica beds, and the oil is passed through it. So all the coloring impurities, minute traces, they all adsorbed, and once they are adsorbed, your oil is pristinely clear and clarified. So it's passed through that, passed through good filters, and what you get is your pharmaceutical grade refined oil. So what you learned today are the chemical methods of evaluation of fixed oils, extraction and the refining of your fixed oils. So here are a few more readings if you wish to proceed with the studies on this, and thank you everyone for patient listening.